Hello, I'm Angélica and today I'm going to present our work named Fracture Behavior Evaluation of Sandwich Panels, Experimental Results and Discrete Element Simulations. This presentation is organized as follows: Introduction, Lattice Discrete Element Method, LDIM, Experimental Campaign Examine, Simulations, Results and Conclusions. In last decades, composite materials have been used in many engineering applications due to their improved properties with respect to traditional materials. Sandwich panels are worth noticing since they are generally lightweighted with excellent properties in terms of load-bearing capacity, thermal and acoustic insulation, and waterproofing. Sandwich panels consist of a soft thick core between two thin sheets, which are held together by means of adhesive layers. Due to the large amount of variables affecting the properties of sandwich panels, numerical models are generally employed for designing practices. In the present work, the lattice discrete element method, LDIM, is employed in order to evaluate the fracture behavior of sandwich panels subjected to bending. In more detail, the LDIM consists of a set of masses joined by bar elements characterized by a regular cubic arrangement. The discretization strategy employs a basic cubic model with 20 bars and 9 nodes, where L is the length of longitudinal elements. The bars are characterized by a bilinear constitutive law which allows to take into account the reversible effects of crack nucleation and propagation. It's a law that considers residual deformations when unloaded. The bilinear law shown in this figure directly depends on three local parameters: the bar-specific stiffness, the ultimate strain, epsilon U, is the strain value for which the element loses its load-bearing capacity, that is, the bar break, and the critical strain, epsilon P, which is the strain at the crack initiation. In LDIM, a random field is introduced for fracture energy, GF, and as consequence, randomness is indirectly assigned to critical strain, epsilon P, through this equation. In this way, the maximum strain of each element Fp is also random. The GF is modeled by a Weber probability distribution. It's assumed that the material fracture energy may be appropriately modeled as a random field characterized by linear space correlation, defined by the three correlation lengths in the coordinate directions. The proposed methodology aims at the simulation of the field describing material properties independently from the mesh used in the LDIM model. A three-point bending test was carried out on a sandwich panel with an expanded polystyrene core and other sheets of composite fiberglass and resin glued to the upper and lower regions of the core. In table are shown the main dimensions of panel. The total length of panel is 2 meters. 3 repetitions of tests were performed. The LDIM is implemented in the ANSYS LSTM environment, allowing the use of both discrete elements and finite elements in a unique model, thus creating hybrid models, named the LDIM. According to the LDIM, the region where the fracture is expected to occur is modeled by means of discrete elements, whereas the rest of the model is discretized by using finite elements. The LDIM model is employed in order to simulate three-point bending tests. In the LDIM, a sandwich panel 2D model is simulated. The upper and lower sheets and part of the core are simulated in fan. In the central region, Close to the surface where the deflection occurs, the glue and part of the core are simulated in LD. In the left support, there is restriction in Y direction, and in the right support in X and Y direction, and the prescribed displacement is applied in the central region. With implemented methodology, it's possible to create different rupture configurations, changing the distribution of random values. 3 cases are simulated to evaluate fracture behavior. 2 simulations with the same probability distribution, case 1 and case 3. These are properties used in simulations. Case 1. Coefficient of variation fracture energy, CVGF, equal 100%. The CVGF refers to each bar. Through calculations performed, a portion of volumetric domain which characteristic length L has an average 14 bars. This implies that the solid CVGF is 2.5 times smaller, so in this case 40%. Case 2 is the same, and case 3 CVGF equal 140% and solid CVGF equal 56%. This figure shows an example of random field dispersion distribution used in the discrete elements of the glue simulation, this part in green. Glue distribution failures are represented by the blue regions, where the specific fracture energy of these elements is lower, making them more susceptible to collapse. This figure shows the collapse form in case 1. Here is shown the first bar breaks red colors in the glue region and is verified that they located where the sheet buckle occurs. Shown in this figure located on the right side near where displacement is applied. Subsequently, the glue damage propagates, blue bars, through the connection region between the sheet and the glue. In this case, a new GF random field spatial distribution is used in the discrete elements of the simulation. This figure shows the collapse in case 2. In this case, the ruptures of the first bars, red colors, occurred in the both regions, glue and core, located where the metal sheets buckle, left side near where the displacement is applied. Subsequently, there is also the rupture of some core bars, located where the prescribed displacement is being applied, showing the form of the collapse present in the experimental tests that consist rupture of the core and the bonding of the sheet. The CVGF can be used as an adjustment parameter in the simulations. In case 3, this increased by 4% in relation to case 1. This figure shows a collapse, and here is shown that the damage occurs initially in the sheet buckle region. Much of the damage occurs in the top 3 models that simulate the glue. But in this case, there is greater damage to the bars that make up the core and are located where the prescribed displacement is applied. This figure shows a comparison between the numerical and experimental results in terms of force versus displacement curves. In case 1, green curve, the rupture load is greater than those presented by the experimental results, black curves. In case 2, blue curve, it can be seen that the rupture load in the simulation is greater than those presented by the experimental results and in the case 1. This case shows the sensitivity of the model to the inclusion of randomness in the material's properties. As seen in this figure, the fracture energy spatial distribution in the glue has blue regions, weak regions, less evident near the region where the prescribed displacement is applied compared to the case 1, making the panel more resistant. In case 3, purple curve, the simulation presents the rupture load similar to that obtained by the experimental results. This fact shows the influence of coefficient of variation fracture energy in the simulations, since the blue regions, which represent the region where the glue is not well distributed, having even lower fracture energy values compared to case 1, where the same distribution is used, leading the panel to fire more quickly in these locations. In this work, a comparative analysis of three-point bending tests in a sandwich panel with simulations performed through a hybrid model of discrete elements and finite elements in the ANSYS LSDine environment was performed. The results obtained with the LD present a behavior similar to the experimental results. Thus, it's possible to interconnect the LD with the fan efficiently for solving problems. The hybrid model made it possible to represent the characteristic properties of the material as correlated random fields in the ANSYS LSDine software, and the possibility of carrying out the union between discrete elements and finite elements will allow, in future works, the solution of complex problems by using the benefits of each method. Thank you, and please, for any questions, contact me by this email.